So today we're going to be looking at the magnetic force being exerted, uh, the magnetic field being created by a current going through a long straight wire. So the equation we're using here, we've got B, which just stands for the uh, magnetic field or the strength of the magnetic field, equals this mu zero, or if you have any microbiology or anything, this symbol here means micro for like a prefix for the metric system. Really, it's Greek letter mu zero. That stands for something called the permeability of free space. Really, it just lets us know kind of how magnetic field strength changes with distance. Kind of huge generalization there. Uh, Capital I, though, is the same capital I we've been working with. That's the amount of current flowing through the wire over 2 pi r, where r is just the radial distance from the wire, how far away um, the object is from uh, the current carrying wire itself. So coming back to this permeability of free space here, mu zero, really, it's just a constant. It's true anywhere in the universe, really, and it's just 4 pi times 10 to the negative seventh. Capital T here is the what magnetic field strength is measured in. That's a Tesla. So it's Tesla meters per amp or per ampere. Um, Really, if we just know the current going through the wire and the distance from the wire, we can actually calculate the strength of the magnetic field. Big thing though is this is a vector. Direction's really important with this. So let's say that I've got a current carrying wire here, and let's say that the current going through the wire is going in that direction. Or if I want to do it a little bit differently, I would say that my current is going in that direction. Now I know, in 3 dimensions, there's going to be a magnetic field formed around the wire. All right. But I know from a bar magnet that magnetic field lines go from north to south. I could have drawn that a little bit differently. Okay. All magnetic field lines are all going to kind of follow the same thing. They're going to go from north to south. There's a direction to them. So to figure out what direction, whether it's clockwise or counterclockwise around my current carrying wire here, it's going to follow the left-hand rule. So essentially what this means is you're going to stick your thumb out, stick your thumb in the direction of the current that the current's going. Thank you, Facebook. And then what you're going to do is you're going to curl your fingers around, kind of around your thumb. And granted, keep in mind, I am not an artist here. As I draw my little demon hand there. All right, so if the current's going that direction, this is called the right hand rule. Got to work on my penmanship there. Okay, so the right hand rule says that if my current's going that way, the electric field is going to follow the direction of my fingers around it. Okay, so if I get rid of the hand part, if my current's going that way, the the magnetic field is going that way around it. Okay. So in this case, with my current going this way through this wire here, I'm still going to do the right hand rule where if I stick my thumb in the direction that current's going, so if I stick my thumb to the right, the magnetic field is essentially coming out of the screen up top and it's going into the screen on the bottom. So to indicate where they're coming out of the screen, that's going to be a circle with a dot in it. Okay, so we're just going to do kind of these circly things. You don't have to do that many. That's probably too many. Essentially what these circles represent are just areas where we're going to test the direction of the magnetic field. All right. So we said that the electric field is coming out of the screen. So essentially to indicate that in the circles, I'm just going to put a dot. That tells me that the magnetic field is coming out of the screen up top. Now to indicate that the magnetic field is going into the screen at the bottom, I'm going to put an X in the circle. And this is just the general scheme that physicists use to kind of depict this. So really, even if I didn't know, so if I saw a diagram and I didn't know what direction the current was going, if I know that the circle with the dots indicate that the magnetic field, I'm going to keep doing that. The magnetic field is coming out of the screen there or out of the paper there, and the X's indicate where the magnetic field is going into. I can simply try to arrange my fingers in such a way that the magnetic field's coming out at the top and in at the bottom, and point my thumb out. That's going to tell me the current's going to the right. Okay, that's just some diagramming that I know I would ask you to do. College, you may be asked to do that as well. So if you're ever asked to diagram, the magnetic field around a current carrying wire, that's just how you do it. All right, so let's actually get to some of the math here. So down there at the question, before I do that, there's going to be several right-hand rules. We're going to call this the right-hand rule for the magnetic field around a wire. Okay, right-hand rule around a wire. Okay, pretty basic, pretty easy. You could also call it the magnetic field right-hand rule. There's a bunch of them, just know that's what this one's for. All right, so let's look at the bottom of their question, the example question I got there. So they want to find the magnetic field or the magnetic field strength at a distance of 1 meter from a long straight wire carrying a current of 1 amp. All right, so essentially we could even reuse this diagram here. We'll say the current going through the wire is 1 amp, and they want to know the strength of the magnetic field 1 meter away from the wire. Doesn't matter north, south, east, west, above it, below it, doesn't matter. They just want to know the magnetic field 1 meter away from the wire. They give us I, that's the current. They give us R. So let's even try to figure this out. So the magnetic field is equal to 4 pi times 10 to the 7th times 1 times 1 amp over 2 pi, and then we're going to go times 1 meters, okay? Because the distance is 1 meter. All right, so let's figure this part out. Probably should have put the units in there. So let's put the units in for the permeability of free space here. Let's go Teslas, meters per amps, just so I can do some unit analysis. Amps cancels amps, meters cancels meters, pi cancels pi. 4 over 2, that's going to be 2. So really what I'm going to find here is, I don't even need a calculator for this one. In fact, pretty much all my numbers canceled. The only thing I'm left with Teslas for a unit, which is good because that's what magnetic field strength is. And then I'm left with 2 times 10 to the 7th. So that's just in scientific notation. So 2 times 10 to the negative 7th. I can write that better. 10 to the negative 7th Teslas. Essentially, the equation's pretty super easy to use. Just got to plug in what you know and then solve for B. Sometimes they will give you B. You have to solve for R, or they ask you to figure out, like, if you want this magnetic field at this distance, what's the current? It's just pretty basic algebra. Just keep in mind the permeability of free space and that 2 pi part. They cancel out well together. So that's a little bit of diagramming rules. That's how the equation works. Practice problems should be easy. Good luck.